Up to this point, we've described what an electrolyte solution is, and we've shown that the chemical potential that we have written in the past for solutions can now be written in a more involved way to involve both the positive and negative ions that appear in the solution for electrolytes. So I've just expanded out results that we've obtained earlier. Now in this I want to specify that we are associating this piece here with mu2 0, which means that the piece that we have here is being associated with this function. So this would be A2. Alright, so what we have here in essence is an identity of the activity of our solute with this interesting powers of plus and minus activities for the plus and minus ions in the solution raised to their stoichiometric coefficients as equal to our activity, our effective activity. Now it turns out that it's going to be useful for us to define a quantity. I'm going to write it over here. V is just equal to the sum of these two stoichiometric coefficients. And one way you can think of V is it is the total number of ions that are placed in solution by each solute molecule. So, for example, if our molecule were calcium chloride, this would produce 3 ions. We would have calcium 2 plus, and we would have chlorine minus and another chloride minus. So we'd have a total of 3 ions, and so this would be equal to V. Alright, so for this reason, it turns out that it is convenient to describe another quantity, which I'll call A plus or minus, raised to this V. And we're going to set this equal to this interesting function of the two positive and negative ion chemical activities. Now this A plus or minus is something that we're going to call the mean ionic activity. In this case, the word mean is not there to indicate a disposition, it's there to indicate an average. So this is in some sense an average of our activities that are due to the plus and minus ions. And I probably should stop underlining them here because it's going to look like a plus or minus that I've drawn here. Okay, so this is A sub plus or minus that is related to these this way. Now I'll note that in fact we could write more explicitly that A plus or minus is going A plus raised to the V plus, A minus raised to the V minus, and then the whole thing raised to the 1 over V power. So in other words, let's take an example. Let's suppose that I have a solution of potassium nitrate. Alright, so this dissolves and forms potassium ions and nitrate ions. Alright, so 1 positive, 1 negative. So our V in this case is going to be equal to 1 plus 1, because I have implicitly a coefficient of 1 there and a coefficient of 1 there, or 2. So my mean ionic activity is simply going to be A plus or minus is equal to the square root of A plus times A minus. So this is perhaps the simplest case. We would say that potassium nitrate here is a 1,1 electrolyte. That is to say, it produces 2 ions that balance in charge. So it could be something like calcium oxide would be a 1,1 electrolyte as well. It would be CaO. Okay, so this gives us a way of defining a new quantity, and this new quantity is now one that we can begin to derive some thermodynamic expressions for so that we can get some understanding of these systems. Now I want to point out another thing, and that is that with activities, we have in the past written them in terms of activity coefficients. We even saw a graph of an activity coefficient earlier. And the way we started with these was to write it as an activity coefficient was a proportionality constant to the mole fraction. All right, and typically gamma, this activity coefficient, is a number between 0 and 1, although it can be greater than 1 also. But it's basically giving us a way of measuring the non-ideality that's captured in the chemical activity here. I shouldn't have put this thing here. It's greater than 0, but it doesn't necessarily less than 1. All right, I want to generalize the one that we're using here to include the activity written in terms of molality. So in this case, we're going to have an activity coefficient, again, that's written in terms of molality, times the molality of the solute. Okay, so when we do this, if we have this as our definition for A2, what are we going to have for our molalities for the two components? Well, here, remember that each A2, or each solute molecule is going to produce V plus of the positive ions, and so that will be multiplied by the molality of A2. So that would be, in essence, what our molality for the positive ions will be. Similarly, the molality of the solute times V minus is going to give me the molality of the negative ion. All right, and using these definitions, I can now also write that the A plus is going to be activity coefficient plus in terms of molality times the molality of the plus ion. And A minus is going to be the activity coefficient for molality times the molality of the minus ion. So these are going to be my working definitions in the case of molality for these chemical activities and activity coefficients. Now, how will these manifest themselves when I'm looking at my definition for A plus or minus? All right, if I have A plus or minus, and I'm going to say that's raised to the V power, that's going to be A plus raised to the V plus power times A minus raised to the V minus power. Or in other words, I'm going to have something that looks like this. I'm going to have M plus times the activity coefficient plus, and I'll skip writing the superscript on here for now. We'll just assume this is all going to be molality activity coefficients raised to the V plus. And then I'll have M minus activity minus activity coefficient minus raised to the V minus. So now if I gather the M's together and the activity coefficients together, I'll have M plus V plus, M minus V minus, and I'll have gamma plus V plus, gamma minus V minus. Now I'm sorry, this looks hideous the way I've written it here, but this is all equal to A plus or minus raised to the V. So now if I take the Vth root of both sides, so I'm going to get rid of this and have 1 over V and 1 over V, taking the Vth root of both sides, I can now associate this part here with a mean molality. I'll write that out, the mean molality for this ionic solution. Similarly, for this activity coefficient, I can write this as, in essence, a mean activity coefficient. And now I have gotten all the way back to being able to write my overall chemical activity, A plus or minus, as simply the product of the molality, the mean molality, times the mean activity coefficient. All right, so we have some nice symmetry here in our formulas, and I hope that all of the pluses and minuses here don't look too forbidding, but really what we're trying to do is preserve the form of the mathematics that we've worked so hard to develop these past few lessons, so that we can understand what's going on in electrolyte solutions and attach some meaning now to quantities like this activity coefficient and this mean ionic activity.